Hi everyone, welcome to the 6-point-B notes. These are going to be a mix of U substitution challenge problems and then some definite integrals. Remember, definite integrals are the ones that actually have bounds. So for this first one, we are given the integral e to the square root of x power divided by the square root of x dx. And so this one is kind of tricky to figure out what is the inside function. And so just remember, basically the inside function, the derivative of it has to cancel out something else in the problem so that we only have e to the u power. And so I would say the natural thing to pick, and so don't write this down yet, but the natural thing to pick for u is probably x. That's a potential thing that you could choose because that is the function inside the square root. But the problem with choosing x is that the derivative of x with respect to u is 1, and that doesn't help us cancel anything out, right? We would just have e to the square root of u power and then the square root of u, and that doesn't help the fact that this up here is a composite function. And so that's actually not what we're going to choose this time. And so we're going to try to choose something else that would actually help us cancel something out. And so that in this case is going to be the other option, which is just the square root of x. And that, again, that is an inside function, right? And so that's actually what we're going to choose here today. And so we are going to go ahead and switch this to exponential form just so we can take the derivative of that. And I'm going to go ahead and find the derivative with respect to x, which is 1/2 x to the negative 1/2 power. And I am going to go ahead and put that back into radical form because I think it will help us evaluate as we go. So that's what we've got. And we've got the derivative du with respect to x equals 1. So we essentially have this equals 1 divided by 2 times the square root of x. And then I'm going to go ahead and solve for dx to help me plug in. And so if I do that, I'm just kind of, I'm multiplying these. I'm kind of just cross multiplying. So I should get 2 square root of x du equals dx. So that's kind of my setup over here. Now I'm actually going to start the process of substituting. So I'm going to go over here to my original function. I had e to the square root of x over the square root of x dx, and I'm going to plug things in. So I know now that it's going to be e to the u power. I'm actually not. I guess you technically could plug in u here, but I'm not going to do that because that would just make a quotient. So I'm going to keep this as the square root of x, and I'm going to multiply that by plugging in. So I plugged this in here, and then I'll use a different color for the next part. For dx, I'm plugging in 2 times the square root of x du. And now I'm just going to do some simplification. So these two things will cross each other out. So I'm going to move the 2 in front of the e. So I get this expression right here. And then I take the antiderivative, and that equals 2 to the eu plus c, and then I have to go back and replace the u back in for what? I got to get it back in the x to be defined by x instead of u. So it'll be 2e to the square root of x plus c. And that's our answer. So that one was more challenging just because sometimes it's hard to know what you should choose for your inside function. So that is the answer here. Next one is the integral of x times the square root of x minus 1 dx. So again, it's kind of hard to know what should you choose for your inside function. So sometimes you're just going to have to mess around with it, but I'm going to choose x minus 1 because really it is the only option I have. Square root of x minus 1 isn't the derivative of that is not going to help us cross off this x. So we're going to go with this, and we're just going to have to kind of work through it. So the derivative of u is du dx equals 1, and so then du equals dx based on that. And so if I go and I try to use my u substitution here, I would have, this is what it originally is, and I would have x times the square root of u times du. And so the problem with that is that this doesn't go away. That doesn't mean I did anything wrong. That just means I have to use a little bit more extra algebra. So remember that u equaled x minus 1. Well, that means that u plus 1 equals x. So what I can actually do is come up to this expression, and then I can also replace that x out front with u plus 1. But again, I've made some progress, right? But I still have a product. But what better way to get rid of a product than by actually multiplying? So before I can actually do that multiplication step, though, let's remember that we like when we have things in exponential form. And then this is what I'm doing with my Algebra 1 kids right now. We're just going to distribute. Remember, this has a 1 on top of it. So I'm going to get u times u to the 1/2 power. When you multiply terms with exponents, and they have the same base, you just add their exponent. So this will be u to the 3/2 powers, because 1 plus 1/2 is 3/2. And then 1 times u to 1/2 is this. And so now you don't have a product, you don't have a composite function, right? You just have some addition and everything's with u. And so now you can actually take the antiderivative. That will give you u to the 5/2 divided by 5/2 plus u to the 3/2 divided by 3/2 plus c. I'm going to first kind of clean up this. This will become 2 to the u to the 5/2 over 5 plus 2 to the u to the 3/2 over 3 plus c. And now finally I need to plug u back in. So it'll be 2 times x minus 1 to the 5/2 over 5 plus 2 times x minus 1 to the 3/2 over 3 plus c. And that is our answer. And if you thought, man, that was terrible, these things couldn't get any worse, just wait for the next one. The next one's the worst one, but then hopefully they'll be a little easier from here on out. So last one, same idea. What did you choose to be u? And your best option in this case is going to be 2x plus 3. And this one is kind of similar. So how do I recognize this? This is similar because I have a 2x plus 3 and I have a 2x minus 1. Both of those, because they're linear functions, we can use some algebraic manipulation to actually define both of them by u. That was kind of the same here, x minus 1 and x. Both of these x's are to the same degree, which is why I could solve for u. This isn't necessarily the same way, but that is why this method right here works. And so again, you just have to play around with these a little bit, but our u is going to be 2x minus 3. And the reason u is 2x minus 3, not 2x minus 1, is because we really have to, this is a composite function right here. And no matter what we do, we have to simplify that down because there is not a composite rule for integrals. There's only u substitution and some other strategies we'll learn later. So just to start off, I will take the derivative of this. I will get 2. So that means that du, right, just solving here. So I'll get du over 2 equals dx. And again, if I were to plug in this expression for dx, that's not going to cross off this 2x minus 1. But if you guys remember, just like the last time, u equals 2x minus 3. So let's go ahead and solve for x here. I would add 3 on both sides. I would get this. I'll divide both sides by 2, and I get u plus 3 over 2 equals x. And so now I'm just going to plug some of this stuff in, and it'll work out great. So from here, I'm going to replace x with u plus 3 over 2 minus 1, and then I'm going to make it square root of u. And then dx is du over 2. So this looks very messy right now. Let's just go ahead and see what we can do with this, clean this up a little bit. Sorry, this 2 here should have been like this. Okay, so let's just clean this up a little bit. This part right here, I'm going to simplify first. So these 2's just cancel each other out. So I'll have u plus 3 minus 1 all over the square root of u times du over 2. So I just crossed off these 2's right here. Let's see what else I could do. I'll make this u plus 2 over the square root of u times du over 2. So this 2 right here really isn't doing anything for us. So what I'm going to do there, it's not going to help us cancel this out at all. So I'm going to go ahead and pull out, dividing by 2 is the same as multiplying by a 1/2. So I'm going to pull out a 1/2 in front of the integrand. And then I will have this expression right here. And so this is still a quotient. So we're what do we do with this? Well, same thing in the last problem. we had a product, and so we actually multiplied. We're actually going to divide here, and we are able to do that, but real quick, I'm going to go ahead and move that u into exponential form. And based on just properties of fractions, what I can do is I can split the numerator. So I'll have u over u to the 1/2 power. Remember, that's a u to the 1 power plus 2 over u to the 1/2 power du. And now I can actually do some division. So this is still 1/2. U to the 1 power divided by u to the 1/2 power is u to the 1/2 power. You just subtract their exponents. Oops, you just subtract these exponents. And then there's no like simplification I can really do here, but remember to use the antiderivative rule. I can't have anything on the denominator of the fraction, so I'm just going to go ahead and pull it up to the top and make it a negative exponent like this. Also, did I do anything wrong? Oh, okay, I made one mistake. It's not really going to change everything, but if you guys notice here, I wrote this u as 2x minus 3 when it should have been 2x plus 3. So then down here, it should have been 2x plus 3. And so then, sorry, we're just going to have to change a couple things, my bad. This will be u minus 3 instead. So all of these plus signs here will be minus signs. So that would make, whoops, just some mistakes. Hopefully someone caught it before I did it. So then essentially these are all going to be u minus 4. So it doesn't really change anything, but my bad. Minus 4s. Okay, keep going if you hadn't made this mistake. You were smarter than me. Minus 4. And this will be minus 4. Okay, we're going to keep going. Sorry, that was my bad. So now everything is good. Everything is like it's just subtraction now. And so I'm going to go ahead and take the antiderivative of all of these. So this will be u to the 3/2 over 3/2 minus 4 times u. So if I add 1 to this, that'll be u to the 1/2 over 1/2. And then again, obviously we do plus c. This is just looking ugly. And so I'm not going to like completely simplify this just for the sake of time, but I just do the one thing I need to do is plug u back in. So u is 2x plus 3 to the 3/2 over 3/2 minus 4 times 2x plus 3 to the 1/2 power over 1/2, and then plus c. And I'm going to stop there just for the sake of time so we can get to some definite integral problems. But that's how you do that one. That one's just like a little bit nastier with the algebra. But let's keep going. So now we're going to do u substitution, but notice that we have some bounds on here. And so the process is going to be pretty much the same, but we just have to talk about how do we handle the bounds and what are some shortcuts we can use to handle the bounds. So for this one, try to decide what you guys think the inside function is. It's going to be 4x squared minus 1. And just imagine taking the derivative of that. The derivative of this is going to be 8x, which that will help cancel out that 3x. So the derivative of this is 8x. So that means that du over 8x equals dx, just doing some algebra in my head. And so that is going to help us get set up. But when we go and we change this, what's happening is we are going to change this function so that it's in respect to u, not x. And these bounds are about the function when it's defined by x. And so this is trying to say find the area under the curve from 0 to 5 when the function is defined by x. But if we're about to change it to be defined by u, we need to use different numbers here. And so what I'm going to do for this is I'm going to go ahead and I'm going to change these bounds so that they're with respect to u, not x. And so u, its relation to x is u equals 4x squared minus 1. And so I'm going to go ahead and I'm going to plug in 0 for x, and I'll get u equals -1. So I'm going to highlight their like connection here. So that lower bound becomes -1. And then the upper bound will be u times 5 squared minus 1. So that will be 100 minus 1, which is 99. So I'm just changing those bounds, and that will actually make the end of our problem a lot easier. So I've changed those bounds. Now I'm going to go ahead and change everything else. So this will be 3x. This will be e to the u power in these parentheses. And then dx gets replaced with du over 8x. These x's cancel out, so I get 99 to the -1 over 3eu over 8 du. I'm going to go ahead and pull out the 3/8. They're just a coefficient and then I just get a nice EU function. The antiderivative of EU is EU, so I'm going to get EU, but then I also have to use my bounds here. So what's nice about this problem is because I changed my bounds to U, and these are like what x equals with respect to u, I actually don't have to plug back in u because I changed my bounds. And the idea of 99 and -1 is going to work through the fact that I changed it from x to u. And so I actually can just evaluate the problem as it is right now. And that's why definite integral problems tend to be a little bit easier because of that. So all I'm going to do is 3/8 times e to the 99 power minus 3/8 times e to the -1 power, and I'm just going to stop there. We don't even need to simplify for the sake of time, but you can simplify that. And you don't add the plus c because it's a definite integral, and the c from the evaluating the first bound and the c from evaluating the second bound would just cancel each other out. So that's that one. We have 2 more problems. Let's see how much we get through. So this next one, our inside function, you probably are going to debate between x minus 1 and the natural log of x minus 1. The natural log of x minus 1 is actually going to help us cancel out the denominator of x minus 1 because the derivative of the natural log is 1 over x minus 1. So that's why we're going to use that. So u is going to be the natural log of x minus 1. And just if you remember over here, like the derivative, so say y equals the natural log of x, the derivative of that is 1 over x. So this is like the same thing. You technically have to use the chain rule, but because the derivative of the inside function equals 1, you don't even really like notice you're using it. So the derivative of this is 1 over x minus 1. And so that means that du x minus 1 equals dx like that. So that's the first work I'm going to have to do. Then I'm going to have to change my bounds so that they're in respect to u, not x. So I'll plug in 2 first. It'll be the natural log of 2 minus 1, which equals the natural log of 1. And I'll just leave it like that. I'm not going to simplify it right now. And you honestly shouldn't, because if you simplify it too early with the natural log, you'll round and you'll change the meaning of your problem. And this will be the natural log of 3. So I'm just changing my bounds to start with, and then I'll go and like plug my u's in. So this will be u squared over x minus 1, and then times du times x minus 1. So replacing that with dx. These cancel out. So now I have natural log of 3 over the natural log of 1 equals u squared du. Now I just take the antiderivative, which is u cubed over 3, and then I just have to evaluate it with my bounds. And look at that, we'll have time to do the last problem. So this ends up being the natural log of 3 cubed over 3 minus the natural log of 2 cubed over 3, and I'll stop there. Okay, pause it if you need more time, but we're going to do one more problem, and this last problem has trig involved, and you're going to love it. So, okay, question is, do we use tangent of x, secant of x, or secant of x squared for u? Well, you might have to remember your derivative facts, but the thing that you need to process through here is, do one of those functions, does their derivative equal the other? And the answer is yes. The derivative of tangent of x is secant x squared. And so that's why we're going to use our inside function to be tangent of x. So solving that up real quick, we'll get du over secant squared x equals dx. And then again, let's work with our bounds to change them. So if u equals tangent of x, tangent of 0 is, remember, tangent is always sine over cosine. So if you forget this, it's sine over cosine. Sine of 0 is 0, and sine of cosine of 0 is 1, so it's just 0. And then if I want to find tangent of pi over 4, again, that equals sine of pi over 4 over cosine of pi over 4, and sine of pi over 4 is the square root of 2 over 2, and so is cosine, so that equals 1 right there. So my bounds are going to be 0 to 1, and then I'm replacing tangent of x with u. I'm going to keep secant squared x in there, but then I'm replacing dx with du over secant squared x. These cancel each other out, so I get 1 over 0 u du. The antiderivative of u is u squared over 2, and then I have my bounds, and so that will be 1 squared over 2 minus 0 squared over 2, which just equals 1/2. And it looks so complicated, and then you get this like really easy answer. So that is U substitution with some more hard problems and definite integrals. I hope you had fun. Have a good day.